Good morning, everyone. Today we're going to embark on an in-depth discussion regarding the concept of hierarchical risk parity. And as our primary resource, we will be making use of the Finance ResearchGate website. So our initial and most crucial step is to ensure we fully comprehend the underlying theoretical principles. So the fundamental idea behind this approach is that we first take all the individual stocks or various inputs and carefully group them together into distinct clusters. Following this, we then proceed to allocate a specific amount of capital to each one of these newly formed clusters. And subsequently, within each of these clusters, our objective is to meticulously determine and assign appropriate weights, specifically possible weights for the different firms involved, all with the primary goal of effectively minimizing the overall financial risk. So, the initial step involves grouping similar assets into distinct clusters. Then, we must assess the risk profile of every single cluster. We're allocating more capital to a lower risk cluster, and we'll continue this process until every single asset has been assigned a specific weight. To illustrate this concept clearly, the most effective approach is to begin by examining a practical example. For our demonstration, let's assume we're working with a scenario where we have 4 distinct assets and a time frame spanning 6 periods. So here we have We're looking at 4 individual assets here, specifically designated as 1, 2, 3, and 4. Now, if you observe, each horizontal row in this display signifies a distinct time period. These periods are arranged sequentially, beginning with 1 and 2 and progressing further. For a primary objective, the very first task at hand is to accurately identify and then locate all of the various companies that are suitable for being placed together, forming a single distinct cluster. Specifically, we are looking for those particular firms that demonstrate a high degree of similarity concerning their return correlation. For example, when we look at them visually, asset number 1 and asset number 2, they appear quite similar. They also tend to move in, the same general direction. Similarly, assets 3 and 4 also look very much alike. However, to accurately quantify and truly understand this entire classing process, we have to employ
the correlation matrix. So let's see.
So, as you can clearly see presented here, we have the return matrix. Following this, we are then able to obtain the variance-covariance matrix, specifically focusing on the relationships between these particular assets.
Precisely 4 assets.
For example, this value here represents the variance of the first asset, and this next value shows the covariance between the first and the second asset. Finally, we have the covariance between the third and the second asset. And we are then able to transform the measure of covariance into a more standardized correlation coefficient, because we understand that this particular covariance value, when it is appropriately divided, for instance, by the mathematical product of the individual standard deviations of those 2 distinct assets, this calculation will ultimately provide us with a crucial correlation. So once we have the standard deviation and the covariance values readily available here, we can then proceed to easily obtain the complete correlation matrix. Therefore, once again, in this specific example, we are considering 4 distinct assets. And here we can see the correlation. And then to determine their proximity, we can calculate the distance between each individual asset by utilizing the correlation coefficient. For instance, if we observe that the correlation between 2 assets is strongly positive, and specifically if it reaches its highest possible value, which is +1, then the resulting distance between them would effectively become 0. This implies that firms which are highly correlated and move in the same direction will inherently be assigned a much lower distance value. In this particular scenario, when we perform the necessary calculations between the values of 1 and 2, the resulting figure that we obtain would indeed be 0.04. This means that the first 2 assets are positioned very close to each other. Furthermore, the distance between asset 3 and asset 4, if we apply this specific equation, would result in a value of 0.08. This indicates a low value, meaning the distance is quite small, which implies that asset number 3 and asset number 4 are also very close to one another. However, the distances measured across different categories or types are considerably more substantial. For example, if you're attempting to establish a meaningful relationship between one of these particular assets and another, the resulting correlation coefficient could typically range from 0.33 to 0.37. So as you see in this particular scenario, within the context of our current example, we will of course be dealing with a total of 4 distinct assets. However, it's important to note that these assets are clearly divided. Here we have one specific collection, and over here we have the entirely separate other collection.
So in this particular case, it's evident that we have 2 distinct clusters.
We have a clear division between asset 1 and 2, and then similarly a separation between assets 3 and 4. We could designate this first group as the upper cluster, for example, and the second one as the lower section. So what we're looking at here is the variance of the very first asset, and then this next value represents the covariance between the first and the second asset. Essentially, this forms a subcovariance matrix, or more accurately, it's a crucial part of the overall full covariance. This is the covariance between the second asset and the first asset. This is the variance of the second asset. Similarly, we have here asset 3 and 4 and 3 and 4. So that would be the variance of the third asset, the covariance between the third and fourth asset, and so on. So, as we previously mentioned, this represents our initial cluster. We've designated it the left cluster since it occupies the left-hand side of our arrangement. Conversely, over here we have what we refer to as the right cluster, which specifically includes assets number 3 and 4. So, we need to allocate capital, determining how much we invest here, and precisely how much capital we should allocate to the most suitable cluster. This particular decision must be our very first and most fundamental step. To successfully accomplish this, it is absolutely necessary for us to calculate the IVP weight. More specifically, these are referred to as the inverted variance portfolio weights. So, for instance, considering our initial portfolio, we're looking at this specific subcovariance matrix that exists between asset number 1 and asset number 2. We then proceed to bring this particular matrix down to this position here. Following that, we'll invert the variance associated with the first asset, which is represented by this specific numerical value, and similarly, we'll also invert the variance of the second asset, which corresponds to this other numerical value. So, we calculate this value for the variance of our first asset, and then this other value represents the inverted variance for the second asset. Following that, we determine the proportion between these two. For instance, this particular number here should be the result of dividing the inverted variance by the total amount of that identical numerical value and the inverted variance of the second asset. What we're looking for is simply the proportion. So if we do that, it's going to give us... Okay, so we have this value here, which is 0.502. That particular value is designated for our first asset. And then moving on, this next value we're discussing, this is specifically for the second asset. So just to be clear, that number, the one we're focusing on now, will definitely be assigned to the second asset. And if we proceed to do the calculation, for the first one, it should be quite the opposite. Why is it the reverse? Because assets with a higher variance should always be assigned a lower weight. So in situations where we initially started with an asset exhibiting lower variance, it was then determined that it should be given a lower weight. Therefore, considering that the first asset we are discussing has a lower variance, it logically follows that it ought to receive a proportionally higher weight. So in our calculations, we specifically utilize the variance value that is related to the second asset, placing it within the numerator when determining the weight for the first asset. Therefore, if this particular variance number happens to be higher, the first asset will consequently receive a more substantial weighting. This approach is adopted because our fundamental principle is to consistently assign a greater proportion of weight to those assets that inherently possess lower overall risk. So after we have successfully determined the weights, to begin, it's essential that we accurately determine the statistical variance for every single cluster we've identified. This specifically entails calculating the variance value for the cluster positioned on the left side, and then, in a similar fashion, also for the cluster located on the right side. The procedure to compute this variance is quite direct. We will simply take the predetermined weights, and then multiply those by the comprehensive variance covariance matrix. Alright, so the very first thing we need to do in this process is to take the transpose of these specific weights. We then multiply that result by the variance covariance matrix, which is represented right here. And subsequently, we multiply it once more by the original weight itself. This essentially means we're multiplying the weight twice to ultimately arrive at the desired weighted square. And that process will then provide us with the statistical variance of the left-hand data cluster, specifically considering asset number 1 and asset number 2. And the resulting figure we obtained was this value. We'll apply the identical process to the right-hand cluster, and this will yield a specific number. It's important to observe that the right-hand cluster exhibits a noticeably lower variance. Consequently, due to this reduced risk, our expectation is to assign a substantially larger portion of capital to this particular segment. The crucial question then becomes, how do we accurately determine the exact amount of capital that has been allocated? Our calculation involves taking the variance of the right-hand cluster and dividing it by the total variance, which is the sum of the variances from both the left and the right clusters. Consequently, if the variance observed in the right cluster is significantly higher, this implies that the assigned weight for the other cluster, the left one, will also increase. This essentially means that a greater variance in one cluster directs us to allocate more resources or focus on the other, less variable cluster. Well, in this specific instance, the variance for the right cluster is quite a bit lower, actually significantly reduced, is raised to the power of -5. The left cluster, however, has a noticeably higher variance. So, the specific weight that has been assigned for what we refer to as the left cluster, or alternatively, the top cluster, since in this context, top is synonymous with the left cluster positioned between points 1 and 2. That particular value only comes out to be 0.16. The fundamental reason for this observation is that the variance associated with the right cluster is significantly lower than the variance of the left cluster, and this particular value represents the weighted investment, or more accurately, the capital specifically allocated to the left cluster.
So what exactly would be the specific weight that is given to the very bottom section? Or perhaps it's simply 1 minus the value of the top section. Alternatively, what is the weight that's going to be assigned to the cluster on the right-hand side?
Consider this calculation. If we take the number 1 and then proceed to subtract the value of 0.1628 from it, the resulting figure that we obtain will be very close to 0.837. Consequently, this indicates that a substantial portion, indeed the vast majority of the overall statistical weight, will be allocated specifically to the cluster positioned on the right-hand side.
And then, for each cluster, we need to know the weights that are invested in every single asset. So in the left-hand cluster, for example, we have 2 assets, specifically asset 1 and asset 2. So how exactly do we go about assigning these particular weights? It's based on the very same underlying idea. We calculate the variance proportion, and it's the variance itself, not the inverted variance. So for instance, in this specific scenario, we would take the degree of variance of the second asset, and then you'll divide that by the total sum of both assets. And that resulting value will represent the weight that's invested in the first asset. Always remember this important rule. When we begin at the numerator with the variance of a specific asset, that particular value is intended to be the weight assigned to the other asset. For example, you can try this out yourself and simply plug in the numbers. You'll take the individual variance and then divide it by the total sum of all the variances. So in this case, we have one number here and then another number right here. You'll notice that the variances are quite close to each other, and this is why we've invested with nearly equal weighting. So that particular value would be the weight invested in the first asset. The weight invested in the second asset then should be equal to 1 minus that, because we only have 2 assets within that specific cluster. It is absolutely crucial that we precisely calculate the product of the capital that has been carefully allocated in order to ultimately derive the final weights. For instance, the initial weight value we've recorded here represents the weight assuming a full 100% investment. However, this isn't accurate, as within the left cluster, we've only committed a specific portion. Therefore, to determine the true actual weight, we must multiply the amount we've assigned to its respective cluster. In this particular scenario, and then we take these values and multiply them by the specific weight that was assigned in our second step, which relates to the internal cluster. And for the very first asset, it was 0.5024. If we do the calculations,
We are probably going to achieve almost this exact number.
we are able to perform the identical procedure for the second asset, the third asset, and indeed the fourth asset as well. So, to summarize this point, the IVP weights are exclusively utilized to quantify cluster risk. This cluster risk then dictates the precise amount of capital that each individual cluster is allocated. However, the singleton variances, representing the variability of individual assets within each cluster, are what determine how capital is distributed internally among those clusters. Notice here that we never inverted the full covariance matrix. We did perform an inversion, but it was simply a straightforward inversion of a single number, such as the variance of each individual asset when we determined the variance for the left cluster and then for the right cluster. That was just a simple inversion of a single value.
We never actually performed the inversion of the variance-covariance matrix.
So, this particular point could certainly be seen as an advantage. Now, we'll apply this concept to the Finance Research Gate website. I'm going to specifically choose the time series. We'll commence our focus on the specific period beginning in the year 2000 and concluding in 2010.
The main input variable for which we are aiming to minimize the associated risk is the monthly return.
And what we need to do at this point is to carefully determine the monthly stock returns for a carefully chosen representative sample of firms. To ensure everything remains consistent and perfectly aligns with the example we've been following, let's specifically select 4 distinct companies. So for example, we'll go ahead and pick this particular firm right here, then we'll also include this other one, and finally, we'll add this last one to our selection.
Go ahead and apply.
We have successfully acquired all the firms.
Then we'll utilize the portfolio section and make sure to enable it.
And then, within the framework of our objective, we need to identify the hierarchical risk parity approach. We also have the concept of equal risk, which is quite similar. These two methodologies could potentially be quite close in their application, so the points we've just discussed were especially pertinent to understanding the risk parity framework.
When we talk about the covariance estimator, this particularly concerns the variance covariance estimation process. If you're looking to shrink that or reduce its complexity, we have a separate YouTube video that covers it in detail. In this particular instance, it might not truly be significant as we are not concerned with the inversion of complete variance covariance metrics. However, regardless of that, we will simply choose the sample 1. And we need to carefully consider the data from the most recent 12-month period to accurately estimate all the critical parameters. These would primarily involve the correlation coefficients, the individual variances of the data points, and naturally the associated covariances that were directly applied within our detailed discussion. So first we need to calculate the correlation to accurately determine the distance, which will then allow us to identify the distinct clusters. Following that, within each of these identified clusters, we will proceed to calculate the inversion of their individual variances. This step is crucial to ascertain the appropriate weight for an inverted variance portfolio, ultimately enabling us to determine the overall variance of both the left and right clusters. So first, we must determine the exact proportion of the variances that exist within each individual cluster. This step is crucial for us to accurately calculate and assign the appropriate internal weights to every single cluster. To achieve this, we will require a sufficient data sample, and for our analysis, we plan to utilize the complete set of 12 monthly observations available to us. If you wish for more, you can certainly increase that amount, and we will be performing this particular process each and every month. So we will not be left with only one portfolio optimization outcome. This entire process will be consistently repeated month after month because we are rebalancing our portfolio every single month. I would strongly prefer to increase this parameter just to ensure that our portfolio optimization process is not overly constrained in any way. So let it freely perform the optimization and then provide us with the optimal solution, fully aligned with the portfolio's objective. There's no need for us to take any special steps here, given that we're only dealing with 4 assets. All right, so let's go ahead and run it. The portfolio has been successfully built. This is the out-of-sample performance. Sharp ratio is nearly 0.7. The annual return achieved was 24%. The corresponding annual volatility measured 31%. These results are actually quite favorable, especially considering we only incorporated 4 individual stocks into our analysis. This will then provide you with a comprehensive table detailing the specific weightings for each individual month, because for every single month, we have the precise outcome of the portfolio optimization process. For example, over the course of the past year, and more specifically within the last month, we have invested in these particular amounts, 0.2, 0.3, 0.1, and 0.8. This represents the proposed weighting solution. So we can also proceed to create an entirely different portfolio.
I believe we should implement the minimum variance portfolio. We are consistently utilizing precisely the same financial instruments, those very same stocks.
This one, I'm specifically pointing to this one.
This thing here and that thing there.
And then you can apply.
Enable portfolio optimization.
We're going to choose the minimum variance.
And now let's go ahead and run it.
You'll clearly observe that in this particular scenario, the overall performance achieved was significantly superior when we opted for the minimum variance portfolio strategy. This is primarily due to the fact that its Sharpe ratio, a key measure of risk-adjusted return, registered a considerably higher value. Furthermore, if you carefully compare its impressive annual return against its relatively lower annual volatility, the advantage becomes quite evident.
If you scroll down just a little bit, then we can actually review the in-sample data.
We need to consider the necessary statistics also for the minimum variance portfolio.
Let's go ahead and apply those filters again. And then we're going to apply again the hierarchical risk parity. Let's take a look at the in-sample descriptive statistics we have here.
The average monthly return that we observe for the hierarchical risk parity approach stands at 1.79%. Its corresponding standard deviation measures out to be 0.0912. In contrast, when we look at the minimum variance portfolio, we actually find that it exhibits a slightly higher mean return and, importantly, a lower standard deviation. All right, so that concludes our overview of hierarchical risk parity. And as I've previously mentioned, a key characteristic of hierarchical risk parity is that it does not rely on the inversion of the variance-covariance matrix. Therefore, if for any reason the covariance matrix happens to contain an estimation error, then hierarchical risk parity would undoubtedly be the superior approach to depend upon. For our specific situation, accurately estimating the variance-covariance matrix wasn't a significant issue. However, in different circumstances, we might find it necessary to rely on the hierarchical risk parity approach. That concludes our discussion for today. Thank you very much for watching.